Introduce Naresh Patel, who's going to tell us all about storage systems in the cloud. There's a long history between Naresh and I. You'll have read his bio probably, and you'll see him as clearly an expert in storage architectures, which is what he is. But I've known him for a very long time, and for example, we wrote our book together quarter of a century ago. Makes it sound a lot, and it is. So he's not just a storage man; he's very much a performance guy as well, and he's all of the architecture that he works with. He keeps performance in mind, as he'll no doubt tell you about. And we've continued collaborating over all these years since he left Imperial College in about 1993. No, earlier than that, only a little bit, the early 90s. So without more ado, I think to give him a chance to give a good length talk and to allow for questions, I won't elaborate anymore or continue anymore. So I'll hand over to Naresh Patel, please. Naresh, you need to unmute. He was there.
Yeah, so we can also see his screen, right?
Yeah, we've got there's the video there, and he's. Can I unmute him? No, I can't. Can you unmute him? He shows us muted. I can send him a text.
I sent him the request to unmute, so.
Okay.
Hi, can you hear me now?
Yeah, good.
Oh, good. Sorry about that. Now we got to work out video. Yeah, now we got to work out video. Are you seeing anything from my screen?
We see just the desk with the Catalina desk. I'm not sure you're sharing the proper screen, Naresh.
Okay. Do you see something though?
No, just the desktop.
Oh, you just see my desktop though. Okay. And that's good enough. Let me see. Yeah, I did a share. Okay. Is that better?
Yeah. Thank you.
Yeah. Okay. Sorry about that. So good morning, everyone. Glad to be presenting today. Thank you for the introduction, Pete. What I'm going to talk about here is enterprise data trends for hybrid multi-clouds. It's going to be a fairly general talk. And specifically, I'm going to talk about a major problem that we have with as Moore's law, approaches physics limits and creates what I'm calling a semiconductor crisis. But really, if we sort of get through, innovate fast enough, then it'll be more of an inflection point. It's not all doom and gloom, as every crisis creates opportunities. So then I'll talk about, possible directions going forward, especially around innovation in the cloud, the AI need for lots of data, and the need for models. So without further ado, let me get started. I have this map. Here's sort of an overall view of the talk, and I'll attempt to go through most of it. These are all the slides I have. And these are different levels of abstraction that I'm talking about. Yeah. Was that a question?
Yeah.
No? Okay. I'll keep going. So what we have here at the top here is layers and lenses that we want to view these things. The layers are these things that I have going across, which are, the tech trends. And I start right at the sort of bottom layer here, tech trends right down to the semiconductor level and the crisis that we're in. And I'll talk a little bit about the components and the three things that we do with data, which is sort of processing, storing, or moving data. Then we go into sort of at a top level, global data, all the data in the world, how much gets created. And I'm going to have a queuing model or queuing view of that. And then some data from real world, our own installed base at NetApp. Then one level below, looking at servers and storage. And I have this theme around process, move, and store for each of those. That's where the Venn diagram is at the beginning of each of these sections. The servers and storage sort of looks at, multiple nodes or compute engines, and so in terms of servers and storage, and how we can put them together differently to sort of, and some of this scale out type approach has already sort of gone underway as we go into more distributed processing and distributed storage. I kind of explain a scale cube, which kind of goes to three different dimensions of scaling. So that's kind of on here. That's a sort of an extension of the servers and storage and how we sort of get around some of this Moore's law. And then finally, I look at, at another level of abstraction, a deeper level at CPU complex. Very briefly going over some of the challenges. This is where, you're moving cache lines around, and through memory, and memory is the storage, and processing is the CPU directly. And then what's interesting here is how we can apply energy metrics, performance trade-offs, and where modeling comes into play. So that's kind of the sort of overview. I'll get started with the sort of layers and lenses. So we talked about the four layers. These are the sort of technology trends: the global data storage, scaling, and properties, server, and then the CPU complex, right? The lenses that we want to apply to these, and so different viewpoints. A lot of the storage is somewhat ignored. The name itself is considered peripheral, and really what the world is sort of really more about the data as becoming more important because AI needs data to do a better job. So data focused is what I'm trying to think about here. And for each of these layers or layers of abstraction, we want to look at the three things that we do to some type of data that's flowing through. And it could be application data, it could be all the way down to cache lines, how we process it, how we move it, and how we store it. And really think about where we do these things today might not be where we do these things in the future. And specifically, that means something like processing, which gets most of the highlight. Can we do it in a different place? Not do it in the CPU, do it somewhere else. Can we do it in memory? Can we do it in storage? And that's sort of the intersections in those Venn diagrams. The other aspect is what I call AI infusion, decision making. And what that's about is what we've done in the past is the hardware designer or the software designer, they make choices whilst they're designing. Pre-compile time design choices are made. And more, we find, and at NetApp, we call them evil constants that we have to come up with. The designers would look at the overall, what the product is and where it sells and what kind of workload is expected. And sometimes have to make some average sort of decisions. And we call them evil constants that put in because it's sort of an average. And probably a good estimate at the time, but, as over time, those get somewhat forgotten. And after some time, you don't know why that constant was created in the first place. But more and more what we're seeing is if we do AI infusion, the decision making can be done much later. In fact, it could be done at real time with the workload that's actually going on with the full experience of what that device has seen in its lifetime. And we'll go into some very basic example of that, of how AI infusion could be used to sort of improve. And I think that infiltrates a lot of the different areas. And I see modeling as a part of that to help that. And finally, as we go through a crisis, there's opportunities. And there's opportunities in performance and energy models and new metrics that we need to now look at. So that's kind of the sort of three big areas that I want to sort of have a lens on these different layers. So let's get started with the basics here. I talked about this diagram. On the left is kind of the layers that we're on. We're at the fundamental layers. I'm starting there at the bottom. I'll go back to the top because that's where the crisis is, right? And the thing to think about here is, how does data get processed, moved, and stored kind of inside components? And what are those components made of? So processing is typically semiconductor and optical. And there's a little bit optical at the interfaces, mainly. Storage has been semiconductor in sort of the memory, on the memory side, DRAM, magnetic for tape and drives, and optical, which is sort of DVDs. Now, more with flash, more and more of the storage is in semiconductor, right? So in terms of what gets stored. And then movement is the network interface cards, the switches, the routers, and most of that is semiconductor, and then the media is copper or optical. The point I'm trying to make here is that all of these are dependent on semiconductors, right? And so anything that sort of changes in the semiconductor world has an impact across the board. And so we'll go into some of that. But given the importance at the lowest level, let's look at the sort of long-term trends that we've had in the past. You've probably seen this sort of chart before in some form or another. I thought this was a good one because it sort of gives you a pretty good history over about 48 years here. You see the straight line, this is the log curve. And you see this nice straight line, which exponential growth of number of transistors, which is Moore's law. Now, I'll have something to say about Moore's law in a minute, but it's a pretty straight line. And it's been growing exponentially for a long, long time. Now, interestingly, over time, things have happened, right? If you look at the single thread performance in blue, around 2004, single thread performance kind of was flattening out. And part of the reason there is the frequency was flattening out. So the frequency is flat after. So what we had was Dennard scaling up to that point. And after that, we could not scale the frequencies as the transistors got smaller. And there's a whole bunch of reasons why, mostly around physics of and power usage. The single thread performance improved because microarchitectures continue to improve, but not at the same rate. It's hard to, double the performance every 2 years, double the capability every 2 years, which is what the transistors have been giving us for so long. The power has been slightly rising, but still flat, relatively flat, because as the transistors become smaller, less power is needed to sort of switch them. And you see again, as we left the single-threaded performance flattened out, the big thing sort of after 2004 was multi-core, multiple cores, and then that's been steadily rising more and more. So we're using up the transistors that we have on the chip by adding logical cores into that chip, and that's how we've been continuing with it. Now, up until that time, 2004, software would just get faster on the next chip because the frequency would be higher and you get more single-threaded performance. Software didn't have to do anything. And so it was a great time. It's kind of the golden era of you get the next chip and the performance is magically much, much faster. Then after that, we had to do multi-threading, multi-core. So to take advantage of an application had to make use of those cores and go parallel. It's still within the chip. And and it's still sort of fairly acceptable nowadays. And then virtualization and containers now can start using the cores much more effectively. And so that kind of drove that. So we're at a good spot. And I think we solved that sort of inflection back then by going multi-core and making use of the transistors. So what's sort of happening now as this moves on? So let's go back to what the benefits are, right? Really, it's all about the cost trends. Moore's law and I call it Moore's law demands, because I think it's more of a goal for the engineers. I think of it as, you've got 2 years, the engineers have to come up with, twice as a density increase of 2x on the new technology, and they have to make it work. And for 55 years, that's what they've been doing. And of course, at some point, doubling for that long every 2 years or so, it becomes more complicated. You end up hitting physics limits. And I'll talk to some of these. The biggest thing is 2x transistors per wafer. These are 300 millimeter wafers these days every 2 years. What it does is assumes that, things get smaller. Now, you can get down to, smartphones and watches, smartwatches. The sizes get very small. So that's more in the consumer side, but it helps everywhere, right? The form factors are much smaller, so it allows some new applications. And some of those drive further investment. Now, the cost per million in transistors is kind of a good metric to follow. Assuming that the wafer cost, the 300 millimeter wafer production cost stays the same, and now you've got twice as many transistors, then the cost per million transistors should go down 50%, and which it kind of has for a really long time. And so now it's cheaper. So not only do you get density, it's cheaper. The other aspect of it is because the smaller transistors, you get less power requirements. So the power, as you go to the next generation, the power gets less as well. Now, all this time, so what usually happens is that you've got a set of what we call process nodes, and you have the leading edge, and you kind of have a bell curve around all those process nodes. As the whole semiconductor industry shifts to the right and starts using the leading edge, and there'll be a new leading edge 2 years from now, and eventually that leading edge becomes the most common one, and then it sort of drifts away after a while because so it's a moving bell curve kind of thing, right? And that's how we've been doing it for 50 years. So this doesn't mean that everybody jumps on the latest one, but looking at the latest what we call a leading edge process node gives you some idea of how things are going to turn out going forward. So here's the chart on the right is a very simple, exponential curve. And what I fitted, the red dots are from Apple iPhones. The latest one is from last month with the iPhone 12 announcement, the new A14 Bionic chip, which is 5 nanometers, really small. The previous one was 7 nanometers. Now, the curve here is, the T here is number of years from a certain point divided by 2, and you're raising it to power 2. So you're doubling every 2 years. There's a scaling on the x-axis here but I put it in terms of years because that's more meaningful to us. And this number, I guessed at the time, but it's probably the red dot, they didn't have the size. I think now I know what the size is. It's 88 millimeters squared. It's a pretty small chip, right? 88 millimeters is less than a centimeter by a centimeter. All these chips are in that sort of range. So they're very small chips. When you think about when the next process is, the next one is 3 nanometers, it's expected in 2022 or late 22, 23. What will that be? There's signs that the 5 nanometer chip, the efficiencies are much less at 5 nanometers. So we'll sort of go into that. So what are the problems? The problems are the cost and power are not coming down as fast as they have been. One thing is the wafer fabrication costs are much higher. The actual fab itself costs multiple billions of dollars to build in the first place. And then the fabrication costs, as you get down to the physics limits, they need, ultraviolet, extreme ultraviolet, which is much more expensive. And the process that they uses 3D transistors, which also is more expensive. So things are not, the assumption that we have that the wafer cost is the same actually no longer holds, which is actually fairly important here, in that, that's what brings the cost down by 50%. And so what the other part of it is that the power aspects of it, the higher resistance of the thinner traces, reduces the power benefits. So there's actually little to no power benefits that we've had in the past. So one by one, if you look at this, all of these benefits are actually going away. And what we're seeing is that some of the chips have dark silicon in them to sort of handle the physical limits, like thermals, meaning that they don't use it all the time. And you know this from, turbo mode. You don't run the CPUs at full frequency. It kind of tones itself down to meet a power requirement. So what does the cost actually look like? So here's just a reciprocal of this curve. So you just compute a reciprocal. I put it on a log curve, so it's a straight line. And the red dots here are the 50% per annum drop. And interestingly enough, this is cost per transistor now. Around, it looks like 2014, the cost started going up. That was a big change for many, many years. And so our 50% per annum drop is now, and depending on how you look at it, is less than 10% per annum drop. And we wonder how it's going to keep going, because the 3 nanometer one is probably going to be more expensive. It's going to have to require new technology to sort of get there. It's always been the case, but we're looking at physics limits where they're really hard to get around. And same could have been said in the past. And I remember people talking about it when we were at 1,000 nanometers. Seemed like a long time ago, but and so we won't get past the 1,000 nanometer. But the thing to remember is that the silicon atom is 0.2 nanometers, and you need a lot of silicon atoms to sort of make. And this is the minimum feature size, and a feature usually has multiple gates, so there's multiple atoms are needed. So we're really getting into a small number of atoms that we're looking at, and just the cost of manufacturing these has already become astronomical. And so what that's caused is a lot of consolidation in the hardware space. And now, some companies have just decided not to drop the leading edge. So Global Foundries a couple of years ago decided that they no longer wanted to stay on the leading edge and just work with the larger process nodes. Which is a real change. It's just one of the smaller players, but they decided there's enough in the market. So that bell curve that I mentioned earlier is effectively stagnated now. And yes, still they're all looking at. Now, it doesn't mean there's no improvements, but improvements go on in the process technology, but not in the way that we've had in the past. So that's kind of the crisis. Let's look at what other ways we can look at Moore's law. So, we're looking around, there's another law that actually came out in 1936, predates Moore's law, by someone called Theodore Wright. And he was looking at the airplane industry, airplane manufacturing. And what he observed was that every doubling of cumulative units produced, the cost to manufacture one unit will fall by a constant percentage. And so if you plot that like this, it sets a curve, and on the x-axis here is the cumulative number of units produced from the beginning, right? So you can imagine that at 5 million units, you're at a certain cost per unit, and you have to build 10 million units to have it, because W equals 1. But then you have to build 20 million units to have it again. And so this is kind of the expression for it. And of course, this sort of, doubling it gives you sort of this formulation. So the 2 to the minus W is the sort of the factor here where you fall, the cost falls. actually a fairly good fit. There's the Santa Fe Institute in San Diego also looked at this and fitted it to a lot of other technologies as well. So what does that look like for us? Well, and how does that map? And it turns out that if you take the unit cost production curve and look at that, how many units are produced per year, you need to have some historical data, of course, here. If the unit production cost is, or unit production is growing exponentially over time, so every year it's growing exponentially higher, then it turns out that Wright's law actually turns into Moore's law. So this is the relative cost here again, same curve, but now it's a straight line, and it's sort of proportional to 1 over 2 to the t minus over 2, again with the w equals 1. That's if it's a linear. That's if it's exponential growth. It turns into the cost curve goes, exponential, negative exponential, effectively. And you know that a negative exponential goes to 0 pretty quickly in terms of the tail. However, in reality, if now we're sort of unit production is growing more linearly, so say growing at 8% a year, still having the W is 1, then you get a different kind of curve, and it's proportional to 1 over t squared. Of course, it takes a longer time to get to 0. So that's kind of the two different curves. And it turns out this is the curve that we're probably going to be following going forward. And it's kind of the inflection point really is the change from Moore's law to to Wright's law, and a parameter. And so it does introduce another parameter beyond, and you need more information about the production. And so the numbers are very large, right? Semiconductor industry is a huge part of the overall industry. The consolidation, you may have heard of the recent mergers from AMD buying, Xilinx, and then NVIDIA buying for ARM Holdings for, many billions of dollars. So what's happening is that the chip designers chip designs are leveraging existing process nodes and not moving on. And, as I said, global foundries have given up on the leading edge because it's too expensive for them. They're smaller. So right now, the leading edge semiconductor companies, there's only 3 of them in the world: Intel, Samsung, and TSMC, Taiwan Semiconductor Manufacturing Company. So there's a lot of consolidation, and a lot of people have given up on the largest one, on the latest node. And of those, effectively only TSMC is the one that builds chips for everybody. Intel, do their own chips, and Samsung do their own chips, or fabrication. But I think some of them might open up more. So really, what does this mean? It means that the opportunities open up. And previously, every 2 years, things were doubling in terms of number of transistors. So optimization of using of those transistors wasn't really that useful, or it might have been useful for a short time, but the engineers are working on the next generation with more transistors. It's easier when there's plentiful supply. And optimizations you make in one design, certainly in hardware, because you're really locked in, you might as well just wait for the next process node, and now you've got twice as many transistors to use. And so optimization and innovation in some ways was held back. Now I think that creates more opportunities. And when you're doing things in hardware, you do have to think ahead and figure out what you're going to do, because obviously it's locked in for a long time. And that's where performance modeling is actually more important, to get the parameters right, and get the right sort of design trade-offs. Now, obviously, there could be new breakthroughs, and it's really material science, and I never doubt that. And I think there will be incremental improvements. But under the covers, this is kind of how I see how things are happening. So, what are the sort of how do we this model matches how the reality going forward to some extent. Let's look at the sort of quickly look at the component trends going forward. So going to the process, I'll quickly go through some of these because there's a fair number of slides here. Moore's law slowing. So in terms of CPU trends, one innovation is to start using chiplets. Now, chiplets are, they're sized kind of like the smartphone chip that we talked about, the A14, about a square millimeter or less, and use many of those and put them on a package, a semiconductor package, rather than using one big monolithic die. Although you've seen, there's another company here that's using the entire 300 millimeter, wafer to build a system. So there's extremes. So there's innovation going in all directions. And of course, as we move on, then there's domain-specific architectures as well, especially in AI. And GPUs are probably the most common sort of domain-specific architecture. But there's AI-specific ones as well that are really good at doing matrix operations, specifically for doing, machine learning. So what's happening with general purpose CPUs? I kind of see that as being a bottleneck because that's the first thing out of all of these that gets hit with Moore's law slowing down. And so what's happening is everybody's going with distributed. The area that we thought was hard and you avoid at all costs because it is more complicated. Instead, we're embracing that, and we're building composable architectures, so we can put architectures together as needed with the right characteristics for the application, disaggregating the resources so that they can be shared, and they're shared across software APIs, so others can use that same API and have access to the same resource essentially on the network, on some kind of network. The scale-out architectures have become popular for both public and private clouds because we kind of need those. There's also scale-up, and the scale-up is sort of how do you make the CPU engines faster? Well, if they're not getting that faster, it's a balance between the CPU, the networking, and the storage. If you do some accelerators and more GPUs, the AI, ML specific, domain specific architectures, there's other offload engines, and we'll talk about some of those for storage and others as well. Then on the memory side, and this is sort of CPU memory, but memory could go on the storage side as well. Persistent memory. Memory-based computing is, if it's synchronous accesses, you get much more efficient programming because you don't have to do an I/O. So not only is it efficient to actually program, it's essentially more efficient from a performance perspective as well. And there's ideas around processing inside the memory. So a lot of these operations that we do in the processor, this is kind of where does processing go? You can do it, some of these things like where you copy memory buffers from one place to another are much more efficiently from not only in terms of time, but efficiency in terms of energy usage. We generally haven't worried so much about energy usage. We just, as long as we've got enough power, I think that's what the usual thing has been for power. But now I think more and more energy becomes a big, issue. And, you look at various data, but, how much energy is being used for data centers, and it varies between 1% and 2%. But this is in a time where we've had, power improvements over time. Now we won't get the power improvements going forward, but the demand is still, and we'll show a little bit later, that the demand is still growing strong. So let's go on to the storage media side of things. Now here, just like, this is DRAM, SSDs, they have very high bandwidth internally. And we're looking for, okay, how can we make use of that bandwidth, somehow, right? They're limited often by the interfaces. So processing inside the SSD is called computational storage. And we also have computational memory, or processing in memory, as it's called. So similar kind of concept. Interesting, storage class memory we can use this. This is things like Optane from Intel and others, others like Samsung ZSSDs. These give you better latency, and there's sort of multiple use cases for this. But as a read cache, seems like the immediate kind of use case to have something that's faster than NAND flash. Specifically, especially if it's a networked and you have a very fast low latency network, you can create very large, multi-terabyte read caches and for newer applications. They can also be used as a write observer because they're persistent. And if you have two layers and the lower layer have less endurance, then with a combination of a front layer which absorbs a lot of the writes and the back end that does not have as much endurance, can you make the whole combination last for 5 years or more? And really, one other way of looking at it is we have a lot of DAS, or direct attached storage, attached directly to the server. Now, if things like power becomes a problem inside the server, you really want to get the drives out of the server. And where, so then it becomes more network attached storage. And so these are network attached. You might start replacing the server side SSDs. So these are sort of the trends of the storage media. This is the standard sort of data access. It's getting fairly crowded. Based on the highest performance SRAMs all the way down to disks and tape, which are the slowest, but they have the best dollars per gigabyte or more bytes per dollar. So this is the range. I think, the main takeaway here is that so there's a dividing line of how you access from memory and how you access from storage. Memory access means you use load store instructions. 500 nanoseconds is kind of maybe the borderline here of accessing things by memory, as memory, mainly because you're holding the processor pipeline. You're holding that creates a problem for too long. And we'll see later that actually a lot of the CPUs are waiting on memory a lot of times for these kinds of workloads. So increasing that memory is a bit of a challenge. Now on the storage side, you're accessing a storage, so you're doing making a request, relinquishing the processor that you're on, and then it requires a context switch to get that back again, get back going again. So latencies can be a little bit higher. Still, there's efficiencies and various things there. We recently shipped our QLC NAND drives, which is quad level, which means that you get 4 bits out of each flash cell. But the endurance is a little bit less, but we're okay with that because of the other tricks that we use. There's 3D X-Point as well, is in an SSD form factor. It's very useful as a cache for lower latency. I think, though, a lot of these are in the middle here. Most of these are semiconductors based. Disk are magnetic based, and tape obviously is magnetic based. And these have their improvements as well. But disks have the challenge of very low IOPS. And whilst the 15K RPM drives have already gone away, the 10K RPM drives will go away fairly soon in the next few years. The nearline SAS, which is the slower, what used to be the SATA drives, those still have an advantage of dollars per gigabyte, and I think they will still stay around. And there's tape, and tape has the advantage that it has, there's no cost to just storing them, whereas drives, there is a cost to keeping them going. So that's why I think there'll be a whole range of these. Flash is playing a big dominating role, though, in terms of IOPS. And growing, continues to grow, taking away all the 10K RPM drive business pretty much, and putting it. And so now high performance hard drives are sort of going away and being completely replaced by, so that's what we'll see in the next few years. And I think 3D X-Point will ramp as well as the prices come down. And some of the DRAM issues that we're having in terms of a bigger memory. But there are challenges because longer DIMMs, they'll probably be on the PCI bus with CXL. The other trend, and the link speeds are growing very fast. And I think the 100 gigabit is, not long ago we were at 10 gigabit, we're today at 100 gig and 200 gig. We're moving fairly quickly. They're matching the PCI lanes, the speeds. So the PCI, we're at Gen 3 right now, we're moving to Gen 4, and there's Gen 5 coming soon. So Gen 3 is 1 gigabyte per second per lane, and Gen 4 is 2 gigabytes per second per lane. And when you have 16 of these lanes to a NIC, so the Gen 4 and 16 lanes matches the sort of the throughput you need for 200 gig. And Gen 5 at 4 gigabytes per second per lane, and 16 of them matches the 400 gigabit port. So really the interconnects are getting faster. The smart NICs to do a lot of the offload, some of the processing, especially around security. Combination of easy programming and data placement benefits of RDMA. So RDMA is becoming more standard. That's all coming together with this. So there's a good ramp still, and there's still the 800 gigabit. I think though at 400 gigabit things will kind of stabilize a bit in the next round. But it's people can only take so much in terms of once they've upgraded their network, they don't want to upgrade it for another 5 years or so. So naturally that. But I think the public clouds are creating faster transitions because they're building so many data centers, and as soon as the dollars per gigabyte per second kind of go down on the next generation speed, they'll start using those, and they'll start using them across the board because it's cheaper, and they can quite easily aggregate and use the bandwidth. The other thing in networking is the connectivity to storage. NVMe over fabrics has become very popular. And this allows scaling, and this is part of the sharing and disaggregated storage. If storage is somewhere, or resources are somewhere on the network, you want a lot of nodes to have access to it. And NVMe over fabric is an alternative to other SCSI-based solutions and SAS solutions to connect. So that's coming up fairly quickly. There's NVMe over fabric over RDMA, Rocky V2, iWarp, and there's also NVMe over fabric over TCP. So once it's over TCP, pretty much anybody, any NIC can connect to it and have storage attached over the network. And so that changes out, and so SCSI. Now, things take a long time to disappear in the storage world, and pretty much especially those that have been around for a long time, the technologies that have been around for a while. So NVMe, the transition from SCSI to NVMe will take some time, but that's kind of well underway on the networking side. Okay, so let's quickly go through. I'm just going to speed up a little bit because of the time we have. The data processing, the data is all over the place. It's on the edge and the endpoint in the core data center and in multiple clouds. And I'm going to look at this in sort of what kind of the applications are what things that are moving. Application and application data are the things that are moving around and need to be processed, stored, and moved. So the real question is, you have this workload for an application, and where's the best home for it? And is it across many of these? So that's kind of a very general question. And sometimes you need the application right at the edge for real-time, low latency. Sometimes you need it in a data center for security and so forth. Right? And you might need it in the cloud because it's cloud native, and you need it for sort of bursting into the cloud. And there's various combinations of these. And containers have become really popular. And maybe the next thing beyond that is serverless and FAS, which is function as a service kind of capabilities. But there's challenges there as well. I'm going to move a little quicker on this one because I want to get to some of these slides. The global data. So here's a way to look at the global data. This is the amount of data. Huge amounts of data gets created every year, and this is sort of the green box here is sort of an idea of 60 zettabytes being created, which is what IDC say is being created in 2020. Right. So this is all data that's created. There's sort of an arrival rate which is increasing. Right. We next year there'll be more than this stuff creating. However, fortunately, a lot of it gets deleted pretty quickly, and a lot of the data, 90% of data are copies of data. This is pretty much everything, and copies of copies of copies. There's a lot of copying that happens. The original data is probably only about 10%. But then there's that little blue arrow. You actually store that. That's actually only 1%. So the Q length is a sort of a measure of the installed base, how much data is actually stored in the world. And that seems to be doubling every 4 years. So, this little box is sort of getting bigger and bigger. And a little cloud, this is how much is in the cloud. So the cloud probably has about 50% of the data. And in 4 years, that's going to be a bigger portion of it. So only about 1% of the data that's actually created here gets into the pool of installed base. A lot of video traffic and so forth just goes straight through. So where do we go from here? Where is the storage? Now, remember I said, we have a problem with, there's a crisis in terms of semiconductors. How are we going to double in 4 years in terms of the amount of data stored? And these are the sort of technologies, you have hard drives, SSDs, non-volatile memory, optical, and tape. That's why I think tape and hard drives are still going to be around because you need some sort of magnetic storage as well. And maybe there's optical storage, and there's other we'll talk about other kinds of storage like DNA storage. Been going on for some time, and but those are still kind of in the lab, kind of areas. But in terms of where we are today, these are sort of the technologies that we have available to us. So that's kind of a problem, and that's part of the crisis as well. Where are we going to store all this data that we create? And sure enough, the amount of data being created is not going down. And there may be some forcing function that we're going to streamline even more, that 1% that gets added to this pool of installed base. But yeah, doubling is going to be a challenge if a lot of it's going to be semiconductor based. It's not going to be cheap to do the double. Because remember, normally, if you're in 4 years, the cost has sort of gone down by a quarter of what it was before, and doubling isn't usually a problem. At least theoretically. And it may not be. The other things have probably gotten more expensive, and doubling becomes not a problem. But if the costs have not come down, and then there's not enough storage. The other thing is to think about how much processing there is to do on all this data and all the movement that we have to do. So there's a lot of opportunity for optimization of all this data and where it's spread out. So somewhat more abstract, but I think this is to give you some idea of the kind of data. So we've been collecting some of this data for our own installed base. And this is kind of a quick chart of all like millions of drives that we have in the field at NetApp. And they're a plot of along their power on hours. So this is one snapshot. And each of these dots represent a drive reads per day. So you can see that they sort of jumping up. They start off when the younger drives, they're a quarter of a year old, start off at very low drive reads per day. And they sort of top out around 3.5. This is a median, by the way, of many, many drives. So we kind of create a set of drives, and then we monitor them over time. So this is an evolution. Now, this is all post-processing. So each one of these dots is sort of, when we first looked at it in that quarter, in the very first quarter, we see a certain drive reads per day for that set, based on how many power on years they've been on. And we go up to sort of 4.5 years here. But then we can look at it in the quarter after that, and we can look at a quarter after that, and we can go for 5 quarters, and this is what the chart looks like. So it kind of says, okay, now we've got an evolution. And we've got about 50 odd metrics and more that we collect from our sort of data that we collect a whole bunch of data, but for this particular study, it was 50 that were collected attributes, and I just plotted one of those. You see some interesting trends. Think, okay, so as the drive ages, there's more drive reads per day. You're reading the entire drive every day, that many times. So you do actually read the data. It's not actually getting any cooler. But then there's kind of a jump at the older, so that's an area for investigation, because between sort of these newer drives, today's drives seem to be a little bit lower in terms of reads, and there may be some reason for that. And maybe they're smaller in size, the older drives are smaller in size, and that's why they get read multiple times. So interesting things kind of come out in terms of, there's also interesting things about wear out if you look at reads, also if you look at writes. So interesting characteristics come out. So the point of this, though, is we're doing this as post-processing. We also do a lot of these drive analysis on the box in real time. Now, the drive itself, and this applies to sort of any device, but the drive itself has am I screen moving on? Hello?
Yeah, it's moving.
It's moving? Okay, just checking. Okay, so this is the one on, because it seemed to be somewhat stuck on mine, but okay. Let me continue with this one then. So this is the chart on data reads per day, and so the idea here is that what can we do on the box in real time, and to make the better decisions about. And this is where the AI infusion comes in. Is we're going to look at this data on the fly and maybe not keep most of it around. That's kind of how we solve the data problem, because there's going to be lots of time series going to be generated, and how do we, and that's where modeling kind of comes in handy, because you kind of want a quick idea about what's going on, and it has to run on the box and has to be fairly efficient. So I think there's a more room for performance modeling there. A nice analytical model, which gives you a good idea, gives you a head start in how to do things. And we sometimes use this too. Moving on to sort of the storage and server, so how do data gets moved around storage. I'm going to speed up here. I did a presentation last week. It's on YouTube for a lot of this particular portion of it, so I'm going to quickly go through some of these. You can look at the YouTube if you're interested in this, but this talks about what types of processing we want to offload, specifically on a particular company called Pensando, which has a distributed services card. And it goes through and provides ARM cores, P4 engines, and hardware engines to take on bulk data and transforms with data integrity. And it has a networking port. It effectively creates another computer system inside your box, and is layered into other boxes that you might have, and resources. Any of these top-level nodes running x86 can access this engine or distributed services across the network. So this is one way of pulling out the processing that's executing and making it more efficient, kind of a domain-specific scenario or architecture. So I'll quickly move on. What we're really doing is we're taking the activity that's happening on the main memory bus, and we're moving it to an outside card. The other part of it is the latencies are, as the variability gets less, there's a quick plot of the half latency knee of these curves. Obviously, as the variability increases, we have lower and lower sort of knee of the curve, and we like to keep below the knee of the curve on these to keep things moving on, especially in the cloud environment, and to avoid long latencies. So high variability obviously hurts, and some of these data transforms actually do impact the variability on the memory bus. I won't go so much into this, but there's vertical scaling is really distributing the compute around, but keeping the data fairly in one place. And so doing the compute outside the x86 is this kind of processing. This is part of the scale cube. The sort of z-axis, that was the y-axis. The z-axis is just creating a partition of the data. So all these little D1s at the bottom here are partitioning the data. And so now you can apply more compute to all of these. If that's not enough, you can go to the x-axis scaling, which is making copies of the data and then having compute operate on that copy. And this is a flash cache approach where you're on-demand caching in a different node somewhere. And it could be inside the same cluster, it could be somewhere else. And that's why I make the performance go higher. So quickly, the scaling in all dimensions. This is the system and the data. You start with a monolithic and you go to sort of splitting by function. This is where functional decomposition comes in. And then we have near infinite scale if you do all three of those dimensions. Okay. I've covered this in another talk, so I don't want to get into that too much. I want to quickly go through the CPU memory complex. So this is kind of going to the lowest level. It's the last part of this, which is, as I said, the bottleneck. What's surprising here, we're looking at cache lines flying around, right? And moving cache lines and storing things in memory. So this is at this level of abstraction. So here's some interesting data from Google. And what it's saying is that where are the pipeline and how are the pipeline instruction pipeline being used and what's the breakdown? You see what's in green is less than 20%. That's doing the somewhat what's so-called useful work. And so when we talk about 100% CPU utilization, under the covers, it's only 20%. When you're at 100% CPU utilization, the pipeline is kind of, but it's 100%, but it's blocked most of the time. In fact, 80% of the time it's blocked doing other things for these real world workloads. And I think we find the same thing in file systems. There's various blockages internal to the chip, and it's what we call front-end bound. There's bad speculation, as you can imagine, but not a lot of that. Most of it is actually back-end bound, and most of that back-end bound is sort of filling caches from main memory. So you're waiting on main memory. This is why we're making a big deal about main memory latencies and making sure that they're nice and low. But unfortunately, with the way things are going, memory latencies have been increasing, and they're likely to get bigger with bigger sockets, right? So that's going to be the challenge. And what can you do about those? That for these kinds of data-intensive workloads, we kind of need to do something about that. And moving stuff away, the data-intensive activity work away from the sort of general-purpose computing, more optimized is kind of one way of doing that, which is what we covered briefly earlier. But moving processing into memory, as we talked about, creates energy efficiency. And then there's the symmetric multi-threading cores. I think probably need more than two to basically overcome the latency that we have in the memory that's increasing. So maybe we need 4 or more. I think Sun used to have a lot more multi-threading than x86. So that's kind of this is a quick chart on energy performance queue. I'm not going to go through this, but there are ways to introduce reinforcement learning. We had a paper on this a couple of years ago, and so I'll skip this one. So going back to as a summary, what we did cover is all these layers and lenses on these process and move and store aspects of data on these aspects. We do have a crisis. We don't think the cost per transistor is going down anymore, and it has been for many, many decades, going down at 50%. So what's happening, and the amount of data, the global data is increasing, and we have to store more. And that's kind of and it's good that we're getting more data because we can do AI infusion. And in the paths of wherever there's data, lots of data, there's some potential for making real-time decision-making using the AI. And in servers and storage, we're sort of in the middle of a renaissance of new topologies, new technologies, new ways of using existing technologies. And so the scale cube sort of gives you a way of sort of scaling data and storage. And then we finally talked a little bit about the CPU complex and some of the challenges inside there as well, so across the board. Anyway, hopefully that gives you an idea of some of the sort of challenges and maybe gives you some ideas about what we could do. So food for thought. I think I'll stop there and see if we have time for questions.
This is Andre. I had a question in Slack.
Oh, okay. Let's see if you let me.
Andre, if you want, you can repeat the question. So please feel free to ask the question directly to Naresh.
I was wondering what language support you envisage for this huge diversity of storage media, or for hiding and choosing it optimally. Ditto for the operating system.
Yeah, which language? Could you be more specific about which language?
Well, not a specific not a language specifically, but it seems to me that the programmer or the system designer is going to have to make choices. And if the hardware is changing behind the scenes, then maybe there needs to be compile time support or runtime support to allow the designer to optimally choose what kind of storage is going to be used. And I'm wondering if NetApps have thought about that.
Yeah, no, that's a good question. I think the way we've been looking at this is the user, the storage admin, is really our end user is our applications that are using this, and we want to hide the underlying technology as much as possible. We're actually going to a point where, you've heard of serverless, where the user doesn't know about the server, doesn't have to configure a relatively new term that we talked about last week at our Insight conference. And storageless is that the user doesn't have to worry about what the storage is. It does not need to configure it. What they need to work at is, the service level objective. What is the service that they need? And that's specified in terms of the latency requirements, the IOPS per gigabyte that they need, the megabytes per second, and bounds on each of those. And that's all they specify. And what we get then is a way to, choose which technology. Now, in terms of the slightly higher level, we want to have a composable system that we can use an application, move that application to an area and have flexibility in terms of where they start. And if they want to go to a different storage, we can move them. But it is actually more of a separate system that's allowing you to do that, more of a orchestrated kind of driven approach. So, how do we opt in? We have a service called Spot by NetApp, which does exactly what it on the clouds for compute and actually storage now. And it has a certain service level objective. And if it finds something somewhere else in another cloud that's cheaper, it'll move the data, but the user doesn't need to know, right? So the suddenly become more useful because it can move them around, and you're optimizing for cost. So sometimes the cost of the compute is like 70% cheaper, or you get it at a third of the price or something like that. If you can use, say, Amazon's idle cycles. However, it means that you'll be the first to go if the primary workload on that increases. You'll be the first to be taken out. Now you want a quick context switch. So this software called Spot by it's called the software, I think, is called Ocean, and it's a company that we acquired fairly recently. It does actually have that. The programmer would provide all the capabilities that we have. At a higher level, an orchestrator would then move around and find the more optimal. So we have the software is actually already there to sort of do those kinds of things.
operating environment that does it, basically.
Correct. Yes. The
Yeah.
operating environment will do it.
Okay, thank you. You've more than answered my question. Thank you.
Okay. Hey, we're running a little out of beyond the time, so hopefully that's okay. Happy to take more questions.
Yeah, well, there are some questions on separate storage and architecture solving with the just the speed and the distinction. There's a blur between what's memory and what's storage, for example.
Correct.
And you gave a couple of examples where modeling was important on energy efficiency, and you can see a need for modeling maybe in the offloading of the x86 to Pensado. As if you're a real need for modeling of the sort of things that this community does.
Yeah. So in terms of modeling, I think there's obviously load balancing, and caching approaches, right? So load balancing and scheduling. So careful scheduling. So what we really want to do is maximize the usage of the resources. So that seems to be the trend. We don't want to use. We want to make sure that any resource that we have, and we're looking at different levels. But if you're looking at memory, for example, you're looking at the bandwidth, internal bandwidth of memory is much higher than what we actually use it from external. If you look at SSDs, there's internal bandwidth that's much higher than the external. So really, if there is all these capabilities, how far do we go? Because there's also scheduling, and I think latency distribution, response time distributions are important as well. Because we have these service level objectives. There's going to be, how do we run these mixture of workloads in this environment? And what if we're stealing idle cycles from some resource somewhere, either a CPU or storage? And we are. But then there's a primary workload that runs on it as high priority. And you have to then context switch out and use something else. Now, a lot of it is somewhat operational, but it's nicer to have a predictive model in the system that runs. To say, well, what's likely to happen? We do this in our we've implemented a half latency rule inside NetApp ONTAP. We already kind of look at that and we say, there's a range of throughput that's acceptable up to some maximum, and the maximum is defined by the half latency rule. However, initially when we get started, we need a model to just sort of say, what would be the response time? Because we don't have any data. So before we have data, we kind of need a quick model just to find out how to sort of size this and how much resources to give. And then once we get more data, we collect histograms of the latency curve. And now we have more of the latency curve. And once we get the full curve, we say, okay, now we can apply this. Useful but I think the simpler models that can run efficiently as a quick analytical model would be useful. Things that are around the response time distribution in that area obviously are super valuable, because the quick computation of these is probably the most important kind of answer. Now, if you have something which takes a long time to compute, I think it's useful to give you insight, and that kind of gives you a different type of benefit. But it's not something that we would run in real time. So I think and sort of marrying that with the AI technology, useful, right? In some ways, sort of using a model to sort of guide the learning, machine learning. So there's various areas here. I think it's a kind of, in the past, as we look at different architectures, as new architectures come about, there's, especially around new hardware architectures, there's always modeling required there. Okay.
Okay.
Hopefully.
That's interesting when what we spend a lot of time doing, and then the dynamic models, which I presume don't need to be so accurate, but they're still useful if
Right.
they're feeding back live information or live predictions. Is that basically what you're saying?
Right. Yeah. I think the distinction is that the live modeling is they both are useful. I think you need the more detailed modeling for specifics in hardware, certainly in hardware design, and somewhat in software design. But software design has a quick turnaround. You try it out. If it doesn't work, you quickly change it and try it again, and you don't really have much time for the modeling aspect of it these days. Especially as you sort of churning out new code every few days. But on the hardware side, it does take time. And so you have a lot more opportunity to do the detailed modeling. But I think on the software side, it's more the live modeling, running the model in real time and getting some answers, which is kind of what we do, right? We do some of that.
Yeah. Probably the more detailed models are probably useful in any case for producing the live models as well.
Yeah, you can start there and then see what's a simpler model. So that would be another approach. It's a good idea. So you start with the what you're happy with, and then see how much of the detail you can abstract away, and come up with something more simple. And maybe just sort of graph fitting, curve fitting at the end of the day. But something is better to turn a more detailed model into a practical model that you can use. Maybe something like that would be useful.
Okay, well, I think we've run out of time. It's not really up to me. I don't know if Danilo's there to hand back to.